Have you ever wondered how a tiny, almost invisible speck of biological evidence can end up being the star witness in a courtroom? Well, today, we're going to pull back the curtain on the science that makes it all happen, and you're going to see why the journey that DNA takes in the lab is every bit as important as the final result. You know, we all tend to think of DNA evidence as this absolute, rock-solid proof. But the truth is, the results that come out of the lab aren't always so perfectly clear. So that leads to a really big question. Why isn't all DNA evidence created equal? Just look at this. On the left, you've got what a forensic scientist dreams of. A beautiful, clean profile. The signals are strong, everything's balanced, it's perfect. But then you look at the profile on the right. Yikes, that's a real problem. The signals are super weak, the data's all imbalanced, and some information is just gone. So what in the world happens to cause such a massive difference in quality?
Okay, let's treat this like a puzzle. We're going to follow the clues, step by step, right inside the lab to figure out how one piece of evidence can end up telling two completely different stories.
All right, our very first clue is something called the CT value. Think of it this way. Before a scientist can even start their analysis, they have to know what they're working with. Do they have a ton of evidence, or are they dealing with just a few tiny traces? So the cycle threshold, or CT for short, is that first critical measurement. It basically tells the analyst how many rounds of copying it took for the DNA's fluorescent signal to pop up on the radar. Now, here's the most important part to remember. It's an inverse measurement. The lower the number, the more DNA you have.
So, if you get a low CT value, let's say 20, that is fantastic news. It means the machine detected a strong signal really fast, which tells you, hey, we started with a whole lot of DNA here. That's the perfect starting point for a great profile.
But on the flip side, if you get a high CT value, maybe a 32, that means the machine had to work a lot longer, run a lot more cycles, just to find a faint signal. This is an immediate red flag. It tells you that you're starting with very, very little DNA, and you could be on the path to one of those messy problem profiles.
And get this. The difference here is absolutely massive. That 12-cycle gap we're talking about, it doesn't just mean you have a little bit less DNA. No way. It means you're starting with over 4,000 times less genetic material. That is a gigantic hurdle to overcome right from the start.
Okay, so our first clue, CT, tells us how much DNA we have. But how does that tiny starting amount become something we can actually see and analyze? That brings us right to the heart of the process. PCR, or polymerase chain reaction. The easiest way to think about it is like a super high-tech photocopier for DNA designed to make billions and billions of copies. But here's the thing, this photocopier doesn't just run on one speed, it has 3 distinct phases. At the beginning, you're in the exponential phase. It's like a brand new copier with full toner and a huge stack of paper, just perfectly doubling the copies every single cycle. Then it starts to enter the linear phase. Now the copier is running low on supplies. It's still making copies, but it's getting sluggish and slowing way down. And finally, it hits the plateau phase. The machine is completely out of toner and paper, the motor's still running, but it's not producing anything new.
And this right here shows you why timing is absolutely everything. That initial exponential phase, that's the Goldilocks zone. It's the only point in the entire process where the copies being made are a true and accurate reflection of the original evidence you started with. It's where the science is just right.
Now this is where things get really, really interesting, especially when you're dealing with evidence from more than one person, a DNA mixture. What do you think happens when our photocopier starts running out of supplies while it's trying to copy a really complex picture? Well, it can actually start to distort that picture.
Okay, check this out, because this is where the science really comes alive. Look at this table. At the very beginning, you have a nice, clear 10-to-1 ratio of DNA from 2 different people. And notice, all the way through that Goldilocks exponential phase, the ratio stays a perfect 10-to-1. But watch what happens as the process keeps going. The DNA that's more abundant, the major contributor, starts running out of toner first, so its copying slows down. By the time you get to the end, the lab report shows a 23-to-1 ratio. That final picture is a total distortion of what the evidence actually was at the start.
So now, with all of our clues in hand, the starting quantity from the CT value, and the story of the amplification journey from the PCR phases, we can finally go back and properly decode the final result. We can read the story behind any DNA profile.
And this is how it all ties together so perfectly. When an analyst sees a really weak profile with low peaks, they can suspect it was caused by a high CT value. They just didn't have enough DNA to begin with. If the peaks are so high they go off the chart,
The sample was probably over-amplified, pushed all the way into that useless plateau phase. See those skewed, imbalanced ratios in a mixture? That's a huge sign the reaction was pushed into the linear phase where the truth gets distorted. And that beautiful clean profile, well, that's the result of having a good amount of DNA amplified perfectly inside that Goldilocks zone.
So the real takeaway here is that DNA profiling is not a black box. You don't just put evidence in one end and get a perfect answer out the other. The process itself, that journey of amplification, has a profound effect on the final profile you see. For a forensic scientist, understanding every single step of that journey isn't just a nice-to-have. It's the only way to tell the difference between reliable evidence and a result that might be completely misleading.
And that leaves us with one last, pretty powerful question to think about. If the scientific process itself can fundamentally change how the evidence appears, then what does a DNA match really mean? It's a crucial reminder that behind every result, there's always a complex scientific story.